Back, guys. This is part 2 of our Introduction to Statistics and Research Design lecture. In this one I want to expand more on the different types of design that exist and ways in which we can measure variables. Okay, so I introduced last time the distinction between descriptive statistics and inferential statistics. Let me expand a little bit about inferential statistics for a second. The idea is that we will be testing a hypothesis. We have a hypothesis about the way a population of individuals compares to another population of individuals, how their behavior differs in some way. And so that may be something like the population of individuals who are under the influence of caffeine versus the population of individuals who are under the influence of nothing, right? And so in other words, how does caffeine affect people in some behavior? That hypothesis is going to say something about a population. But we've already talked about how it's difficult to study an entire population. And so we're going to study a sample and then extrapolate or infer based on what we see in the sample about how that population behaves. So let's talk a little bit more about that hypothesis then. I want to be very clear that a hypothesis is not a question. You may have a research question that drives your interests, but at the end of the day, the hypothesis is no longer the question. It is the statement. It is the prediction. It is, in very many ways, how the independent variable will affect the dependent variable. Okay? Now, you don't want to phrase it as the IV will affect the DV. You want to actually say what those things are. So, for example, it is expected that participants who consume caffeine prior to learning a list of words will remember more of those words than participants who do not consume caffeine. It says how the groups differ, both in terms of their group composition and in what we expect to observe between them. One group gets caffeine, one group does not caffeine. We expect to see the group with caffeine remember more words than the group who did not consume caffeine. Notice that the hypothesis is not, how does caffeine affect memory? That's your research question, not your hypothesis. Once you have a very specific hypothesis, you now have a testable view. You can go to the data, you can observe your groups and say, do these numbers, do these observations comport or fit with my prediction, or do they argue against my prediction? That, as its core, is hypothesis testing, and that's what we'll do for the latter half of this class. So I talked about transforming numbers into, observations into numbers earlier on. The term for doing this is what we would call an operational definition. It says exactly how you're going to measure a particular variable. In other words, what operations, what actions or behaviors must we see or measure in order to count it as an example of this behavior, whatever it might be. So let's say you were measuring anxiety. Well, one way of measuring anxiety might be through what we call skin conductance, where I put electrodes on your skin and I measure the degree to which your skin is currently sweating. Very, very minute amounts, but that difference tends to go up, right? You tend to be more conductive, more sweat produced when you're feeling anxious or nervous. So that's one measurement I can take. That one would be operationally defining anxiety as more or less in skin conductance. Another way might be to define anxiety as a self-report measure and simply say, how anxious are you feeling right now on a scale of 1 to 100? Give us an indication of where you feel in terms of your overall degree of anxiety. Okay? Now, let's say you had a different research question. Maybe, and I'm guessing several of you out there have this question, why do I have to take this class? I am a psychology major. I do not want to take math classes, but here I am in a damn statistics class. Well, so let's figure out, why do you have to take this class? What does it mean? Why do you have to take that? Well, probably, I don't know, you can correct me if I'm wrong, but you might be coming at it from the question of, will I be learning anything worthwhile in this class for my personal career, my own increase in knowledge, anything like that? Will the effort I put into the class yield any personal benefits whatsoever? Okay, that's getting closer then. Now we can start to talk about effort and benefit. So perhaps, maybe get more specific, have previous students at this college benefited from learning statistics? Now we've got a population of interest. Previous students at this college benefited from learning statistics, right? So we can now talk about the benefits. Now we can go survey the alumni. We've taken a broad research question, and we have carefully chipped away at it until it became more and more specific, until we knew exactly how we were going to measure that particular construct. Excuse me, why do I have to take the class? Well, the survey of alumni, this many alumni suggested or said that having taken statistics, they were better able to do this in their job, or they were better qualified to do this in postgraduate work. Or this percentage of students said it did nothing for them and they never used it again ever, right? My point is simply defining your variable in terms of those specific observations that we will use to quantify that construct. So let's get an example of that. I want you to think about these. Don't just listen to me. Look at them ahead of time and think about how you might study these various conceptual variables, these constructs. How are you going to measure gender? Right? We certainly can do this genetically, but that might not capture the full range of that variable. So perhaps self-reported gender. We just leave a blank and let you write it in. Or we give you a lot of different options and you pick which one best classifies how you feel about your gender. Either way, how you define it affects how you can collect that data. If I only put male or female as options in a self-reported gender, or I only use some genetic test for that, I am going to limit potentially the range of gender that exists out there. How about who uses ATMs the fastest? Let's say between older adults and younger adults. Do older adults use the ATMs the fastest? They've been using them for a lot longer than younger adults. They should have a benefit in that skill practice. Whatever your hypothesis is, how do you measure the fastest ATM use? Well, I don't know how you came up with, but the easiest I can think of is just simply sit there with a stopwatch at a safe distance so they don't think you're stealing their PIN. And just say, as soon as they put their card in, you start the watch. Or as soon as they cross a line that gets them close to the ATM, you start your watch, and as soon as they walk away from it, you stop it, and then you record. Older adult, this fast. Younger adult, this fast. How are you going to define older and younger adult? Well, now you got to operationally define that one too. So again, you really have to think about how you're going to define your variables. How about willpower? Willpower seems to be the ability to maybe concentrate, but also to resist the pull of something. So let's say you used to be a smoker. Right? How much willpower do you have? Might be how long you can go before you feel like you have to have a cigarette. To that end, how do we measure the level of cigarette smoking? Well, this one's probably easy if we just count the number of cigarettes someone smokes in a day. Some variables are more easy to define in a way that seems like a valid measurement than others. Level of caring by administrators. How much does your dean, your chancellor, your provost of the University of Michigan Dearborn, the chair of the department, how much do these administrators care about you as a student or about me as a faculty member? And how might I measure that? Would it be a valid measure to simply say, I'll count the number of emails they send me? Does that really mean they care about me? I'm not really so sure that would be valid, but it is one way of operationally defining the variable. Here's one we could all attest to back when we were still in campus learning. How bad the parking problem is at UM Dearborn. Well, I think the easiest way to do this is simply self-report variable. How bad is the problem? 1, no problem. 5, worst problem on campus, right? May not be the best, certainly may not be the only way, but it is one way of operationally defining that variable. Level of joke-telling ability. The lady here in this picture seems to be pretty high on that because the guy over there seems to be pretty damn laughy and amused by her joke. If that's the case, then do we say number of smiles or volume of laughter? I don't know about volume of laughter. My wife's really loud. So when she's happy, she's just loud as shit. But she's loud even when she's not really happy. So I'm not sure volume of the laughter is necessarily a good indicator. How about number of friends? How many people are following you on Twitter? Is that a good indicator of your number of friends? How many people are on your Facebook feed? How many people do you still contact now that you can't actually physically see them? What is the best indicator of your number of friends? I'm not telling you which one's which. That's not my point here. It's simply to say how we define our variables is important, and the operational definition is the term we use for giving these constructs a specific definition about how and which behaviors will be counted, right? How they'll be measured. So let's look at a hypothetical experiment. Let's say we're looking at the effects of cocaine on specific regions of the brain. In order to figure out which regions of the brain respond more favorably, differently to cocaine, we take microscopic amounts and we inject it into different regions of the rat cortex. Okay, let's just call them 1, 2, 3, and 4 as 4 different areas of the cortex. Right? We also have randomly assigned a large group of rats to 1, 2, 3, and 4. Right? We didn't take the dumb rats and put them in 1, and the smart rats and put them in 4. All random assignment to make sure that any weird differences that exist in our population of rats is spread throughout our groups evenly. Right? It's called random assignment, something we'll come up to in just a second here. Then we simply measure how long they stay awake. Right? So we give them the injections and we see how long they stay awake. Well, we are saying the effects of the drug on arousal are measured by seeing how long a tired animal will remain awake. That is an operational definition. Right? We are measuring arousal by how long that animal will stay awake. Confounding variables, well, I mean, honestly, we don't know how tired these animals were to begin with. What if one group was more tired than another? Or if just some across various groups were? Well, that could be a confound or an extraneous, depending on how it was done. The independent variable, what's being manipulated here? Which area of the brain we place that cocaine in? Areas 1, 2, 3, and 4, right? What's being measured? We are measuring arousal. We've operationally defined it as how long that tired animal stays awake. We've talked now about some confounding and extraneous variables. What hypotheses are there? Well, at least as a what we might call non-directional hypothesis, it's that cocaine delivered to different regions of the brain will have different effects on arousal. We might say more specifically that cocaine delivered to the frontal cortex of the rat will result in the highest degree of arousal. That's a very specific, what we might call directional hypothesis. But both are possibilities because they predict a very specific relationship between the independent and dependent variables. Okay, so this sort of brings up the idea of research design, because in that study I talked about how we took a whole bunch of rats, a population of rats, and we randomly assigned them to groups 1, 2, 3, and 4. Okay? Random assignment is what we do to avoid the individual differences that might occur ending up in just a singular group. So what if I was measuring arousal and some of those rats in that larger group of rats were simply the kind of rats like maybe you are, where they can stay up till 5, 6 in the morning and barely feel tired. Right? If that's the case, we don't want them to end up all in one group, because then, regardless of whether the cocaine had any effect or not, they're going to seem very, very aroused, right? That's going to be a confound. And so random assignment is done such that those rats would hopefully be distributed across all of our groups, making it so that they don't have a particular influence on any of them, and it's more of an extraneous variable. That's really important. It's especially important in things like drug studies. In drug studies, we oftentimes don't want participants to even know which group they're in. So going through all of these vaccine trials, nobody in the vaccine trial is allowed to know whether or not they got a vaccine or they got a placebo. So you are walking around potentially with no protection whatsoever, thinking you might be protected, hoping you were in the vaccine group, but it turns out you're in the placebo group. Why do we do that? Well, it's because we have placebo effects. The group that receives the placebo sometimes shows the same benefit or change in behavior as the group that got the treatment, right? The experimental procedure, the drug, whatever it might be. The healing power of laughter and optimistic thinking. If that really does have an effect, then potentially getting a placebo but thinking I got the drug might cure me in the same way that getting the drug might cure me. If that's the case, then the drug really doesn't have any effects, and only by putting it into a single blind experiment where the participant does not know whether they got one or the other, can we rule out those placebo effects. In fact, there are experimenter biases as well. So it's entirely possible that, let's say the doctor who checks up on you after you've received the vaccine, what if they know whether you got the vaccine or the placebo? What if they know and they ask you and interact with you in different ways because of that knowledge? If that's the case, then we need to take that influence out, because it's entirely possible that their interaction style changes your outcomes and your behavior. And so in that case, we do what's called a double-blind experiment. And that's the gold standard, the hallmark of these vaccine trials in particular, where neither the researchers interacting with the participants nor the participants know whether they've received the placebo or the vaccine. Only the statistician somewhere at the computer knows that information. Right? This helps to avoid what we might call demand characteristics as well, where the participant sort of guesses the hypothesis and inadvertently changes their behavior because of those cues. Right? That's not what we want. We want them to behave naturally. So, what are some benefits to random assignment, and why would we want to do this as opposed to, say, self-selection? Why would you let me randomly assign you to these two groups instead of me just saying, here, pick which group you want to be in? Well, let's say we wanted to know whether or not playing video games. So my wife and I like to play a lot of Minecraft. My kids play Minecraft and a bunch of other games, and they all got Doom and Assassin's Creed and a brand new Switch and a whole bunch of shit for Christmas, and so we are video game wacko right now. Will playing video games affect other eye-hand coordination? Could they affect laparoscopic surgical skills? That's eye-hand coordination almost definitely. Will people who play video games be better at laparoscopic surgery? Well, self-selection. Let's say we're going to give you a laparoscopic surgical skill test, not on a person, of course, right? That'd be unethical. But something that might try and assess how good you would be at this particular ability. So I put an ad in the paper and I say, come, let's measure you. I want people who play video games regularly and people who don't play video games regularly. The problem is that these individuals may have chosen to be video game players or non-video game players because of some pre-existing benefits in eye-hand coordination. Maybe you already had really good eye-hand coordination when you first played a video game, and that's why you liked playing the video game. So it's not that the video game led to better eye-hand coordination, which leads to better laparoscopic surgical skills, but really that better eye-hand coordination was already there ahead of time, right? And that's part of the problem of self-selection to groups. Instead, we need to randomly assign. We grab a whole bunch of people, maybe people who've never played video games at all, and we put half of them into a group that is going to play video games, and another group that will continue to not play video games, and then we measure their behavior. Then we measure their surgical skills. In this case, any pre-existing differences that might exist in the population, like differences in video game experience or other experiences, are randomly distributed across these two groups. And instead, the only thing that we know to be different between the two of them is whether they get experience or not experience with playing those video games in our experiment. Okay, so that's important.
In this video, we will be talking about the placebo effect, control groups, and the double-blind experiment. A placebo is known as a fake treatment. It could be known as a fake pill, drink, lotions, or any type of treatment that is known to have no medical effect. However, a placebo may have psychological effects. These psychological effects are known as the placebo effect. By believing and expecting something to work, it will work. For example, if you believe that a pill will make you feel better, then it will make you feel better, even if the pill is fake. In other words, the pill is a placebo. If you think that the same placebo will make you feel sad, then it will make you feel sad. This is the placebo effect. Placebos can be used for a control group. The control group receives the placebo as a treatment. In other words, the control group receives a fake treatment. Now, why would you want a control group? A control group gives you something to compare your results with. So suppose an unknown company were giving pills to people at the gym to help them gain strength. After 1 month of treatment, 75% of the people taking the pills report that their strength has increased. Does this mean that the pill was the cause? No. So far, this is an observational study. We cannot say for sure. Maybe there are lurking variables that are present, like diet and the type of workout routine. Some people may have better diets or workout routines, which may have allowed them to become significantly stronger than everyone else. This is why we need a control group. We could randomly assign participants into two groups. One group will be the control group, and the other group will be the experimental group. Each group will have to get the same thing. So each group will receive the same diet, each group will have the same workout routine, and each group will get the same amount of sleep, and etc. The only thing that is different between these two groups is that the experimental group receives a pill and the control group receives a placebo. A good placebo should look and taste like the actual pill. If the percentage of people in the experimental group significantly gain more strength than the people in the control group, then we can say that the pill is actually the cause for gaining strength. You can think of the control group as just doing nothing to it. We have the placebo for humans because we can perceive things psychologically. If instead our experimental units were plants, which lack a nervous system and the ability to perceive things psychologically, then we don't really need a placebo. So the experimental group of plants receives the treatment and the control group gets absolutely nothing. And then we would compare the results from the experimental group and the control group. Going back to our first example, if the control group knows that they are receiving the placebo, then this will obviously eliminate the placebo effect and it may skew the results. We need an equal playing field, where neither group knows if they got the placebo or if they got the actual treatment. To prevent bias in the manipulation of results, the experimenter should also not know which group is which. This setup is called the double-blind experiment, where the experimenter and the subjects do not know which of the groups being studied is the experimental group and which of the groups is the control group. The double-blind experiment is good for eliminating biased research results.
That also brings up the difference between a couple of different types of research design. So in a true experiment, and we're looking at the manipulation of an independent variable and seeing how it affects a dependent variable, right? How these two groups perform differently on something. We can choose to measure two entirely different groups of people. So in the vaccine example I've been talking about, you can't give somebody the vaccine and then later on give them the placebo. You can't give them the placebo and then later on give them the vaccine. That you need two different groups of people, a sample that gets the vaccine and a sample that gets the placebo. These are completely different groups. They're completely independent of one another. No matter what this group does, it doesn't affect how this group performs. That is what we call a between groups, or sometimes called an independent samples design. Okay, I apologize for the confluence of terms. This is the nature of statistics, unfortunately. It's also the case that we might measure a group twice. So in the group that got the, let's say, the vaccine, we might want to measure them right after they got the vaccine to see how they feel, and then again at 6 months to see how they feel, and then again at a year to see how they feel, and again at 18 months, and so on and so forth. In this case, that same group of people is being measured on the same things multiple times, right? Every single thing we wanted to measure them at time 1, at time 2, time 3, time 4, time 5, that variable of time, distance in time from the vaccine is manipulated within the groups. In a between groups, our variable is manipulated between them. This group gets the vaccine, this group doesn't. And within groups, say time point now versus a year after, that's a within groups design where we measure the same people at multiple time points. Now we do have to worry about order effects. Order effects mean that the simple order in which you measured these different things matters. So let's say I wanted to see how fast you could run the mile, then how fast you could jump rope, then how fast you could do 50 push-ups, and then how quickly you could do some simple math problems. After those three physically demanding things, you might be a little tired and more slow on these math problems. But it's not measuring your true speed at math problems, it's instead measuring your true speed at math problems after these three other tasks. That's what we'd call an order effect. It can also be a practice effect. So maybe I want to know how well you are riding your bike. And so I ask you at 4 years old how well you're riding your bike. I ask you again at 6 years old how well you're riding your bike. And at 8 years old, and at 10 years old, I find that 10-year-olds are better at riding their bikes than all other groups. Is it because 10-year-olds are different from all other groups, or is it simply that you just got better and better and better because that's how practice works? If that's the case, then those latter measurements are sort of contaminated a little bit about that by that practice effect. And so we have to rule out practice effects and order effects in within groups designs. We don't have to worry about that in a between groups design. So let's take that within groups design of measuring the speed of running, speed of push-ups, speed of jumping jacks, and then speed of solving some simple math problems. If we did it in that order, we talked about how these math problems were going to be affected by the order effects from having done all these other things, what we might call a fatigue effect, in fact. In order to see the true way that we perform on this task, or on any of these other tasks, because they all are subject to the order in which they occur, we have to do what's called counterbalancing, where in one way, all participants go in this order. But in another group of participants, we mix up the order, and I can't really do that with my fingers very well, but we mix them up. And they do a math task first, and then these other physically demanding tasks after that. And then another group, we mix these tasks up, and this one comes in the middle, and I'm going to break my finger trying to demonstrate this, but the point is we try and manipulate all different possible orders of each of these levels, and we give them to different smaller groups of that larger within group sample. Right? That's called counterbalancing, and it should help to rule out order effects and practice effects, fatigue effects, and things like that. I'll show you later on that this can get rather unwieldy when you have a large independent variable that has many levels of it, but we have a technique called Latin square design that helps us with that as well. Okay, correlational designs. We're going to talk about this in the next unit of the course, but it's important to note here because correlational designs are neither really between or within subjects. Correlational designs just look at two different measurements, two different variables, and see whether or not they seem to change together. So if on one particular day, Jon Snow found this many deaths, and on the next day he found this many deaths, and on the next day he found this many deaths, and he also happened to be tracking, let's say, temperature outside, if they were moving together in some way, deaths went up as temperature went up, or deaths went up as temperature went down, then this would be a relationship between the two variables. It's not saying temperature caused it, right? We know damn well that even though deaths are increasing right now as temperatures are dropping across the northern hemisphere, it is likely not being caused by that. It's caused, in fact, by a lot of external environmental factors like holidays and people getting together when they shouldn't be, and quarantine fatigue and all these other sorts of situations. So because these two look like they're related, that can lead to illusory correlations, right? Where we see the two as necessarily then being meaningfully related, causally, in fact, related, when they probably aren't. So the correlation that you might observe that big city folks are not as nice as those in the country, right? I'm from the South. People often talk about that Southern hospitality and Southern charm. I'll tell you, although you may have observed that in a handful of cases to the point where you believe in that relationship, it is not causal. It does not mean that if you were from the North and you moved to the South, you would suddenly become a nice person and suddenly have this Southern charm, nor does it mean that someone from the South would move up here and suddenly lose that edge. Not to mention, I'll tell you, as being from the South, not all Southerners are nice. Being now living in the Midwest, not all Midwesterners are not nice. It's an illusory correlation. One of the ways we try and test these relationships is by looking at those boundary outlier conditions that don't seem to fit. So Snow found that the largest number of deaths were right around the pump. Right around that pump in the center of that London neighborhood. So we concluded, based on the correlation, that distance from pump increased, number of deaths went down. It's a negative correlation because one variable went up, the other one went down. So he observed that and thought that might be causal, right? It may be that the closer you are to this pump, the more likely you are to drink from that pump, and thus that's the way that people are dying and getting cholera. But then he saw these outlier cases. There was a London woman and her niece who no longer lived anywhere near Broad Street. In fact, I believe they had lived outside of London at this time, but I don't remember the details of that. And both her and her niece died. And Snow found out about this case. He said, well, that's way off of my map. How did these people die? Another one, a brewery right across the street from the well, as close can be. None of its workers died. These are outliers because they don't fit that relationship. They don't sit with the rest of the data. They're way far apart. And so he looked into these in what's called an outlier analysis. Find out why they're outliers. See if it tells you something about that relationship. Well, it turned out the London woman had previously lived near that Broad Street well. She had lived there long enough that she had grown accustomed to the particular taste of the water from that well. And even after living somewhere else, she would send her niece periodically into town to collect water specifically from that well. So her niece collected the water. The well had been tainted. She brought it back to the London woman, and both her and her niece died. Can you guess why nobody at the brewery died? Well, if you work at the brewery, you have something you can drink other than water. Something that's undergone an entire boiling and fermentation process that will eliminate any of those bacteria. Right? And so again, he was able to find out why these outliers occurred and show that they did not affect the meaningful pattern that was there within the data that he had collected. Right? And then Snow saved a ton of lives by just removing that pump handle. And that's a great example of how simply looking at numbers, looking at the patterns of the numbers, and knowing how to investigate the numbers that don't fit with the pattern, how to interpret cause and effect based on patterns that you see, how important some of that can be in true life-changing ways. Okay, it's a bit of a soapboxy ending there. Let's get a quick summary. Descriptive versus inferential statistics, right? Big differentiation. Sample versus population. After that, we start talking about measuring constructs. How do we measure them? Sometimes in discrete measurements, individual points on a scale, sometimes continuous where we have a full, unending, infinite breakdowns of smaller points and smaller points on the scale in between all those points. We talked about scales of measurement, watched a little video on that. We then talked about independent, dependent, confounding, extraneous, noise, and operational definitions of variables. Moved into reliability and validity, and then talked about hypothesis testing, random assignment, single and double blind designs, placebo effects, demand characteristics, experimenter bias. I didn't put it on here, but that fits in there as well. Between versus within subjects experiments was sort of our wrap-up discussion. Order effects and counterbalancing that we see in within subjects designs we don't have to worry about in between subjects designs, but between subjects designs are more costly because we have to study more people if each group has to be different people. And then lastly, we finished up with correlational designs and Snow's rather famous outlier analysis to determine why the people at the brewery didn't die and the woman outside of London did. Okay, so that's it. I'm going to tack a quick little video on the end here that kind of hopefully summarizes all this in a nice little encapsulated form. Watch it now, watch it later, don't watch it at all. It's entirely optional for you guys. I just wanted to put it in there because I liked the way that they described some of these constructs. All right, till next time. Cheers.
Statistics is often hailed as one of the most useful areas of mathematics. It helps us to make educated guesses of the unknown and find useful information in an ocean of data. But despite its usefulness, many people struggle with statistics. What is it? How does it work? For many, statistics feels like an unending collection of rules and formulas. Even worse, if it's misapplied, statistics can lead to false conclusions. This causes some people to develop a mistrust in the subject altogether. So, what is it all about then? Well, statistics is the area of mathematics which primarily deals with collecting and analyzing data. Some great examples might be keeping track of your favorite team as they rack up wins and losses, or perhaps using data to try and predict the outcome of an election. To be more specific, statistics can be broken down into the areas of sampling methods, descriptive statistics, and inferential statistics. In sampling methods, we cover how we collect our data. This is arguably the most important area of all of statistics. It's important because it ensures that we collect our data in just the right way so that we can make valid conclusions later on. It also helps us know when we have just enough information for further analysis. Remember that even if you use the best formulas and techniques, a study can quickly fall apart if you do not collect your data in just the right way. Descriptive statistics is about summarizing or highlighting important aspects of our data. When people think of statistics, they often think about this area. The tools here are about describing the information you have collected, and tasks such as graphing or calculating a simple average all fall under the area of descriptive statistics. Inferential statistics is about making predictions from our data. Here, the goal is to take just a small bit of information, analyze it carefully, and then see what conclusions we can infer about the bigger picture. It is this part of statistics that can seem the most mysterious. But in reality, it's one of the most powerful and allows us to find even more information from the data we've already collected. Now, when you take statistics, you may find that there are many other topics that don't seem to fall into these three areas. That's because statistics is not complete without exploring why the formulas and methods actually work, or more importantly, when they should be used. For this reason, other topics like probability form a healthy part of any statistics course. Think of these other topics as the framework and foundation that allow us to build so many other useful tools. Lastly, when taking statistics, you may find that you need a little bit of help. I'm not talking about your friend who happens to be great at math, I'm talking about using a calculator or a computer. Although at some level, many of the formulas can be very simple, using them for even a handful of data points can quickly become tedious and cumbersome. The good news is technology can really help with the required calculations. Remember, even though you will certainly become familiar with using technology, you will still need to know when a tool needs to be applied or what method is the most appropriate. Hopefully that sheds a little bit of light on the subject of statistics and motivates you to learn a little bit more about it. In this video, we covered what statistics is and its three main areas of focus. We also pointed out that technology can be your ally, but in the end, you have to make the decisions. Thank you for watching. Did you enjoy watching this video? Don't forget to hit the like button and then subscribe to my channel. As always, you can find all of my videos free of charge at mysecretmathtutor.com. Again, thanks for watching.